Hello, ladies and gentlemen. My name is Dirk Leister. I would like to give you a short overview on twin screw compounding for filament production. Spooled filament polymeric materials for 3D printing come in different classes. So typical materials are base polymers like PLA and ABS, but can also be available in higher engineering polymer grades like PEEK. What is of utmost importance to the quality of the end product is that the filament diameter on the spooled material is kept in very tight tolerances throughout the whole length. But with the development of even more demanding applications, the base polymers might not have sufficient properties. So custom compounds are required more and more to fulfill that need. I have listed here two examples of compounds that have been recently introduced to the market. For example, high-filled polymers with metal powders like a 316L stainless steel. After printing, these parts undergo a debinding and sintering process, leaving only the metal part behind. Or for medical applications, we have PLA and titanium dioxide filled composites that have been used for medical scaffolds or for bone replacement. So to do these custom compounds, we need to do a complete twin screw setup, as we see here in the picture. Everything is based around a benchtop extruder on the right-hand side, sitting one or two more feeding devices for the powders, like the base polymer and the fillers. Then going more towards the left, we have the melt pump, which we come to details in a second, the cooling water bath, and then to the very left, we have the takeoff device for the spooled filament and a laser measuring to ensure the quality of the filament diameter. So what is going to happen inside the extruder? So we do have here a cross-section of an extruder barrel with the different components and sections in it. So the flow of the powder is from the right to the left. So we have the feeding section where we infeed the polymer and or the additives. Then the intermeshing co-rotating screws transporting these into the first plastification zone. Then we have the opportunity to have a secondary feeding of our materials, a mixing zone, more conveying zones until the end where we're venting any volatiles out of the compounded material, and in the extrusion section where we press the material through the orifice producing the actual filament. So this twin screw compounder is a very, very good mixer. So this mixing in the twin screw compounder is so versatile and so flexible because we have a segmented screw design as showed here. On a hexagonal shaft, we are able to move conveying and mixing elements in consecutive order and really building up a screw with mixing and conveying sections as our polymer requires. With the different angles of the mixing blocks, we can actually also control the amount of mixing energy that goes into the process, and we can really prevent degenerating of any material that is heat or shear sensitive inside that process. But all these mixing capabilities, they come at a cost, and this is that the twin screw extruder per se has a pulsating output. And if you remember, the diameter of our filament is of high importance. We need to find a solution for that one. So when doing filament directly from a compounding process, a melt pump is necessary, as been shown here in the picture, attached right to the extruder. So the melt pump uses two closely meshing gears that rotate and then separates on the inlet side of the pump. We see a small picture on the down right side here. This creates a cavity and a suction that is filled by the melt coming from the extruder. The melt is then transported by the gears to the outlet side of the pump, where the meshing of the gears displaces the melt. Since the mechanical distance is very, very small, the melt is effectively prevented from leaking backwards. And the rugged construction of the gears and the housing allows high pressures up to 700 bars, and thus the ability to pump high viscous melts. And by And by controlling the speed of the melt pump, a very accurate pulsation-free output can be maintained, and this resulting in a high tight tolerance millimeter diameter. What we see here is an experiment to depict this. So we choose a high-density polyethylene and producing a strand, a filament, by 3 different means: by a single screw extruder, by a twin screw extruder without any melt pump, and by the twin screw extruder with a melt pump. So the diameter we used here was 1.75 millimeters, and everything was measured by a laser gauge. And as this graph, the output of the single screw extruder and the twin screw extruder and the melt pump, they differ considerably. The twin screw extruder by nation, as we said, this graph shows that the output of the single screw extruder, the twin screw extruder, and the twin screw extruder and the melt pump considered differently. The twin screw extruder by nature has a high fluctuation, as been shown here in the blue graph. So in the last slide of my presentation, we see the single screw extruder filament and the twin screw with melt pump filament, that they are very similar in the tight tolerances, and we meet the specifications here. So using a melt pump and a twin screw extruder enables us to firstly compound a custom-made polymer that is not available on the market, and in one go producing the filament for our 3D printing application. With this, I would like to hand over to my colleague Fabian Meyer so we can learn more about the rheological behavior of these compounds.
Yes, hello and welcome also from my side to this webinar presentation. My name is Fabian Meyer, and in the next couple of slides I will talk about the benefits of performing rheological measurements with polymers that are used for 3D printing, or to be more precise, that are used for fused deposition modeling, or short FDM. So rheology is the study of flow and deformation of matter, and that includes, of course, also all types of polymer-based materials. Polymer melts are so-called viscoelastic fluids that show both viscous as well as elastic properties. And the highly elastic properties that are present in many polymer melts can lead to different types of flow anomalies that can create problems during many processing techniques, including FDM. Now on this slide, you see a schematic drawing of the FDM printing process on the left side with the essential components of the printing device. The polymer is fed into the printer in form of a solid strand, usually coming from a larger drum, and the 2 counter-rotating rollers are pushing the material into the liquefier, where it's molten and then flows under the pressure of newly fed sample from above into the narrow diameter nozzle. Once it exits the nozzle on the opposite side, it links to either the base plate or the already printed part of the final product. By either moving the upper part of the printing device or the lower base plate, the final product is created layer by layer. Once the polymer exits the nozzle, the temperature is usually decreased below the solidification point in order to prevent further flowing and to keep the desired shape. From a rheological point of view, especially the transfer of the polymer melt through the narrow nozzle is of interest, and it's illustrated in more detail on the right side of this slide. The flow can be described as a type of capillary flow and is presented here with an idealized laminar flow profile. In reality, we can assume that for a relatively short nozzle, the flow field is not perfectly laminar and shows disturbances, especially at the nozzle entrance. But for a first estimation of the shear rate inside the nozzle, we can use the equation shown on top of the drawing, which is representing the capillary flow of a non-Newtonian or viscoelastic sample. In this equation, Q represents the flow rate and N the degree of non-Newtonian or shear thinning behavior. Now, for a polymer that is processed in such a way, it is important that its viscosity is not too high, but not too low at the same time. If the viscosity is too high, it will be difficult for the printing device to create enough pressure to put the material into the nozzle and create a continuous stream at the exit of the nozzle. If the viscosity is too high, on the other hand, the material will flow way too fast through the nozzle and no precise dosing is possible anymore. So the correct viscosity of the sample at the given shear conditions is usually adjusted by the nozzle temperature. Rheological measurements can be used to measure the shear rate depending viscosity of a polymer at different shear rates and at different temperatures. We are looking at the shear rate depending viscosity of a single polymer melt, and here we usually observe a shear thinning behavior. At low shear rates, polymer melts still have a Newtonian plateau. This constant viscosity is often referred to as zero shear viscosity. Once a critical shear rate is reached, the melt viscosity will start to decrease. The average number of entanglements or temporary cross-linking points that are formed between the individual polymer coils is decreasing with increasing shear rate. Now this plot is a master curve of a polystyrene melt. This viscosity curve can be divided into 3 different segments. At low shear rates, we see the constant shear viscosity that is linked to the molecular structure of the polymer. At medium shear rates, the viscosity starts to decrease, and we observe a transition with a decreasing slope for viscosity as a function of shear rate. The width of this transition depends on the width of the distribution of the molecular weight. The broader the distribution, the wider is also this transition range. At higher shear rates, the sample exhibits a constant decrease in viscosity with increasing shear rate. This is the range that is important for many technical applications and processing steps. We see here the typical shear ranges for classical polymer processing techniques. And FDM can usually be found in a range between 100 and 1000 reciprocal seconds. Those are the shear rates a polymer melt is exposed to when flowing through the narrow nozzle of a 3D printing device. This slide illustrates different measurement techniques for viscosities in different shear rate ranges. In order to create a complete viscosity curve that covers all the 3 ranges that we have discussed on the previous slides, different measurement techniques or methods are available for the different shear rate ranges. Standard shearing tests with the rotational rheometers do usually only give access to the zero shear viscosity range. For viscosity at higher shear rates, traditionally, measurements techniques that utilize capillary flow are performed. These techniques include measurements with instruments like a classic melt flow indexer, but also channel flow tests with specific dies in an extruder setup. However, for most thermoplastic polymers, the widest shear rate range can usually be covered when performing multiple oscillatory frequency sweep tests at different temperatures and utilizing the time-temperature superposition principle, as well as the application of the so-called Cox-Mertz rule. And this is exactly how the plot that is shown here was obtained. And as we can see, it includes viscosity data over a very wide measuring range with all the relevant ranges for most technical and processing applications, including FDM. So far in this presentation, we were talking only about the rheological testing of polymer melts. But a rotational rheometer can also be utilized to perform dynamic mechanical thermal analysis, or short DMTA. This is usually performed on solid, rectangular-shaped polymer specimen. During a DMTA test, a material is exposed to an oscillatory mechanical excitation while the temperature is continuously changed. The obtained data is used to identify characteristic phase transitions, such as the glass transition or the occurrence of melting and crystallization within the polymer matrix. In addition, DMTA can be used to determine final product performance or to interrogate relevant application-based properties such as stiffness, brittleness, damping, or impact resistance. On this slide, you see the so-called solids clamping tool that consists of an upper and a lower clamp, each of them equipped with 2 moving jaws. And these jaws here were modified by means of a triangular vertical groove along the center axis. These grooves assure a maximum grip for specimen with a round profile, such as filaments for 3D printing. The picture on the right shows the rheometer setup with a solid clamping tool and a PLA filament attached to it. On this slide, now we see the results of two DMTA experiments carried out with PLA filament used for 3D printing application. Let's start with the fill symbols. The test was performed over a temperature range from 30 to 160 degrees centigrade. At low temperatures, the material was in its glassy state and showed high values for the storage modulus, G', the red symbols, and the loss modulus, G', the blue symbols. In this state, G' reached values of around 10 to the 9 Pascal and was about 2 orders of magnitude larger than G'. Up to a temperature of around 60 degrees centigrade, G' remained nearly constant, while G' was increasing continuously. At 65 degrees centigrade, G' reached the maximum, which can be considered as a measure for the glass transition temperature of this material. With a further increasing temperature, both moduli dropped almost 3 orders of magnitude into a rubber elastic plateau. And now the surprising part happens. At temperatures between 90 and 100 degrees centigrade, the values for both moduli started to increase again rapidly, before reaching another plateau. At temperatures above 140 degrees centigrade, the sample started to melt and those values were decreasing again. The increase in moduli between 90 and 100 degrees centigrade can be assigned to a phenomenon called cold crystallization that occurred above the glass transition and below the melting point. Cold crystallization only occurs when the original specimen was processed in a way that included a rapid cool down from melt into the solid state. In those cases, the PLA chains do not have enough time to align and form crystalline domains before reaching the glass transition temperature. Below the glass transition temperature, the mobility of the molecules is reduced so much that no further crystallization will occur anymore, and the PLA shows a dominantly amorphous structure. Now let's have a look at the unfilled symbols. They represent the results of a DMTA test performed with a PLA filament with a different thermal history. Prior to the test, the specimen was heated up to 130 degrees centigrade, so above the cold crystallization temperature, and afterwards cooled down below the glass transition temperature, but slowly with a rate of -2 centigrade per minute. It can be seen that in this case, no cold crystallization occurred anymore, and the material showed no thermo-rheological behavior, or showed a thermo-rheological behavior that is typical for semi-crystalline thermoplastic materials. So what we can see from these examples is that rheological measurements can be used to obtain information about the degree of crystallinity and the thermo-rheological history of a material. Now, the degree of crystallinity, as well as how rapidly a semi-crystalline polymer is recrystallizing once it's cooled down from the melt state to below the melting point, or even the glass transition temperature, is an important information for many technical processes, including FDM. Once the molten polymer is leaving the printing nozzle of a 3D printing device, the temperature is dropping and recrystallization can occur. The kinetics of the recrystallization process can have an effect on how well the newly printed material is connecting to the upper layer of the already printed part. And with this, the rheological part of this presentation is completed, and I will hand over to my colleague Simon Welsmiller for the next part of the presentation.
Thank you, Fabian, for introducing me. Welcome to the third part of this webinar, where I want to talk about X-ray related techniques and how they can help you with your analytical problems. Feel free to reach out to me by using the email address given on this slide, and if you are searching for additional resources, follow the links. First, I want to give you a brief introduction into X-ray diffraction and the unique features of the EQUINOX product line. Maybe you can remember your physics class back during your school time. There was an experiment with a laser scattered at a grating. if we now go down to atomic scale, we can observe something similar for X-rays. In a solid-state compound, planes of atoms act like a diffraction grating, which yields constructive and destructive interference, which leads to peak of scattered intensities. This will give us a direct indication of the 3D arrangement of the atoms. The EQUINOX product line uses a very unique setup to detect these diffraction patterns. We are using a big band gas discharge type detector, and the sample is placed in the center of this detector. Everything is static, nothing is moving, and we detect the intersection of the diffracted beam with the detector. By doing so, this yields a typical diffraction pattern, which you can see on the bottom left of the slide. This is a silicon sample with 60 seconds of exposure time. During this presentation, I want to focus on two techniques, namely X-ray diffraction and X-ray fluorescence spectroscopy. The combination of these two techniques is very useful for quality control if you want to control the composition, the type of the alloy, and also the crystalline size of your materials. The first example I want to show is titanium 6-4 powder, which was provided by a customer. So it's an out-of-the-shelf sample coming from an R&D lab. The expected composition of this alloy is shown in a table on the top side of the slide. We now tested the chemical composition with our energy dispersive X-ray fluorescence spectrometer on the raw powder using helium atmosphere and our standardless UniQuant fundamental parameter approach. We detect some deviations from the specified composition. Namely, the aluminium concentration is too high. Additionally, there is far too much iron and also some chromium, which is not specified. So this could be due to cross-contamination between batches during the melt spraying process, which is used to produce these type of powders. With X-ray diffraction, on the other side, we can detect different crystallographic structures, and we can also see oxides, for example, because they also exhibit different crystallographic structures. For titanium 6-4, we expect an alpha titanium phase, which is stabilized by aluminium, and a beta titanium phase, which is stabilized by vanadium. And if we now have a look on the diffraction pattern shown on the bottom of this slide, we detect only the alpha phase, but no beta phase, and we can see some vanadium oxide. And by means of a retread refinement, we can also quantify it to some 3% of vanadium oxide. This could be due to oxidation during the melt spraying process or by aging of the powder. The second example I want to show is a stainless steel cube which was printed. In this case, we measured longitudinal and transversal to the printing direction because the steel may contain some austenitic iron. This could have an influence on the mechanical properties, and therefore you have to heat treat your samples afterwards. In this case, we detect some anisotropy because in one direction there is no austenite, whereas in the other one there are some 1.3 weight% of austenite. So therefore, you can plan for your heat treatment process by directly analyzing your diffraction pattern. The EQUINOX instruments are also well suited to measure polymers. This is because you can easily measure any type of sample in reflection or even in transmission, as shown on these on the pictures on this slide. This enables you to measure polymer filaments or parts, and besides of the, for example, degree of crystallinity, it's also possible to measure additives and to even quantify them. In this example, we measured aluminum and titanium dioxide additives in a resin matrix. By means of a hole pattern Rheological refinement, we can directly refine the amorphous content, which is due to the polymer, and also our solid additives. We cross-check this by X-ray fluorescence spectrometry, and the results are in very good agreement to each other. For the last part of this presentation, I now want to hand over to Bart, who will give you some information about electron microscopy and computer tomography. Thank you for your attention.
Good morning, good evening, good afternoon, wherever you are. My name is Bart Winarski. I am a staff scientist at Thermo Fisher Scientific. Today I'm going to talk about 3D printing in metals. I'm going to focus on multi-scale, multimodal characterization of printed parts. Here is the outline of my talk. I'm going to place attention on powder stock inspection and quantification, sample preparation and cross-platform transfer using dedicated holder kits, transfer between X-ray micro-CT and dual beams, plasma FIP and laser PFIP. I'm going to present correlative workflow for additive manufacturing, and this will be supported with two examples of direct laser deposition of Inconel 718 and selective laser melting of a medical scaffold made of titanium 6-4. This graph shows volume of material analyzed versus voxel dimension resolution. It contains different length scales or feature sizes. We populated different tools that we offer that covers all the length scales. At the macro scale, we have metrological HeliScan micro-CT overlapping with laser PFIP, Hydra PFIP, and gallium FIP. At the nanoscale, these systems overlap with transmission electron microscope. It is worth to mention that the volumes and resolutions are overlapping, so this allows tracking region of interest from one system to the other. This is possible since introduction of the plasma FIP systems, because there was a gap between micro-CT and a FIP. Arrows on this graph shows directions of sample transfer between instruments. Here are the goals of the correlative microscopy: tracking samples and region of interest, co-registration of various imaging modalities at all length scales, enabling automation of correlative workflows, increasing the data yield from specimens and ROIs, reducing time to result, enabling new science or insights, and data archiving. The key factors for a controllable AM builds are the powder stock parameters like size distribution, composition, powder conglomerates, the AM operational parameters and post-build quality control, dimensional measurements, defect investigation, etc. For the powder stock quantification, we have Phenom Particle X AM desktop microscope for rapid statistics and powder size distribution, shape and compositional analysis using EDS detector. I'm going to use the same graph to show sample sizes that can be prepared for various instruments using different methods. Mechanical cutting, like diamond saw or diamond wheel, or a wire. These are well suited for preparation of samples for micro-CT and large samples for laser PFIP. Then we have electric discharge cutting, laser ablation, PFIP milling. These two systems can produce not only samples for themselves, but for small samples for HeliScan. In this case, we can create different samples like pillars, bars, plates, slice and view blocks for in situ and ex situ experiments and micromechanical test specimens. At the smaller scale, we can use PFIP or laser PFIP for preparation large TM lamellas or small TM lamellas for transmission microscopes or for STEM detectors in a dual beams. It's worth to mention that mechanical cutting and electrical discharge cutting are well suited for removing excess material for laser PFIP study. For sample mounting and a transfer between metrological micro-CT and a dual beam, we introduced two holder sets. Standard one, which contains sample holder, micro-CT post, and plasma FIP or dual beam adapter. Here is the position vertical of a sample and a hole in a micro-CT. Sample is mounted using conductive glue. When it's transferred to a dual beam, sample is mounted using adapter and positioned horizontally. Special design allows us accessing all the ROIs by rotating the sample holder by 90 degrees. Advanced Correlative Holder Kit is designed for 3D study, serial sectioning, EBSD, EDS. It contains similar components but has a different design. Here is the position of a sample holder with different samples in a heliscan, and here are different free position of the sample holder in a dual beams. Again, we can access all the planes by 90-degree rotation of the holder on an adapter. For correlation of coordinates between CT to dual beam, we use special design of correlative fiducial introduced on a sample holder that are easily tracked on a dual beam platform with the MAP software. The design is compatible with inner glass transfer systems as well. Correlative workflow for additive manufacturing. We start with the powder inspection, then manufacturing, then sample preparation, usually by cutting out smaller samples. After that, we mount the sample on a cross-platform holder, either standard one or advanced one. Then we do the CT scanning on a holder, and after that reconstruction. Next, the sample is mounted on an adapter and inserted to a dual beam. Here we use MAP software for sample navigation and co-registration with the micro-CT data. Reconstructed data is analyzed in Aviso, where we search for the region of interest for further study using dual beams. From Aviso, we generate 3D TIFF stack containing region of interest that is transferred to the MAP software. MAPS reads the 3D TIFF stack, and we can correlate micro-CT data with the SEM data using 3-point or 2-point alignments. Of course, we can extend this workflow with a transmission electron microscope. Now let's have a look at first example results of the Inconel 718. We start with a full sample scan of a component with shrinkage cracks. The correlative analysis allows us finding a crack tip. After finding a crack tip, we use PFIB to extract small chunk for further ex situ study with a high resolution. We collected thousands of serial sections. At certain position we collected EBSD and EDS maps. We found the cracks are formed on the grain boundaries in a region enriched with lava phases. We also observed pores of a different size and a region enriched with niobium. We didn't observe typical melt-pooled structure but long columnar grains in the whole build. After serial sectioning, we use AutoTM software to extract TM lamellas to do TM study. Next, we cut small sample from the bigger part using diamond wheel, and we use correlative holder to do the correlative study. These examples show visualization of a CT scan with a high resolution with embedded serial sectioning data. Note that crack continues from micro-CT to auto-slice cell view volume. Further, we blended all the CT scans together with a slice in view using plasma FIB and using laser PFIB. At the bottom, we can see serial sectioning results using laser PFIB. And now we can add PFIB volume serial sectioning. Here is the second example of Type 64 medical scaffold. This build is designed for fatigue testing. Using correlative microscopy, we analyzed as-built sample. We can see geometric deviation of the build from the cut model. We can analyze porosity, quality of the build, and distribution of thicknesses of the struts. On average, the struts are thicker than designed one, and we see small struts being weak spots of the build. From the full sample scan, we found location on a strut having pores in it. We resected the strut using PFIB and we mounted on a holder to do high-resolution CT study. Here we see the summary of the results. Envelope scan with 5 micron voxel size, local scan with 1 micron voxel size, and after this study we did serial sectioning using PFIB to reveal details of the pores and microstructural features of the Ti-6-4, together with surface features on a strut. Metrological HeliScan, Helios platforms, and transmission electron microscopes are ideal research solution for correlative multiscale tomography of additive manufacturing components. HeliScan brings a new era of metrological micro-CT. PFIB systems are essential link in the correlative workflow. Our study correlates multiple and multi-scale 3D imaging modalities to reveal complexity of additive manufacturing components. Presented by thermoscientific multi-scale imaging solution and workflows are flexible and support excellent understanding of various aspects of additive manufacturing. And last but not least, coming soon we will have a paper published in Microscopy and Analysis considering laser PFIB correlative microscopy of 3D microstructures from nanometers to millimeter. Stay tuned. Thank you for your attention.
Hello everyone, and thank you for joining our session today. I would like to open the Q&A session by thanking our presenters for the insight they gave us into the topic of tools for additive manufacturing. And we will now start 10-minute Q&A session. Please feel free to send us your questions and we will try to answer, if not all of them, then most of them. So I start with the first question in the queue. How does using a melt pump increase the quality of my produced filament?
Yeah, this is Dirk here. I guess that question goes to me. Thank you. As I showed in the presentation, there are different methods to produce the filament, and one of the most commonly used is the one using polymer pellets and giving shape to them using a single screw extruder. But when you think about doing a specialized compound, that means you would have a compounding, reheating, melting your polymer, then cool it down to pellets. And then using the single screw extruder, you reheat the pellets again and make the extrusion. So you have a heating, cooling cycle multiple times. And as we heard later on, that can be detrimental to the quality of your polymer because you have a recrystallization that you don't want. So if you use a melt pump, that gives you the chance to produce your filament directly from the composition and omitting unnecessary heat and cool cycles, and therefore getting a higher quality to your polymer. Thank you.
Great. Thank you very much. The next question, is it also possible to add liquid additives to an extrusion process?
Yeah, this is Dirk again. Hi, that's the next question. Yeah,
right.
Sure. When you saw the extruder barrel, I mean, that's the reaction chamber where the twin screws are working in. There are lids on top of it that can be unscrewed and screwed. And in exchange of the lid to close it, you can have an opening either for a dosing a powder or a special opening with a small inlet funnel to put a tubing on. And there's also the possibility to have liquid additives manufactured into your polymer compounds. Yeah, that's very well possible.
Thank you very much. I have the next question for Bart. The automated particle analysis on SCM, is it applicable on Versa 3D?
Okay, thank you for the question. Yes, I think it would be possible to do that, but we can follow up on this question as well for more details.
Okay, I will mark this. Thank you. The next question is how much sample is required for an XRD measurement?
Yes, here, Raphael. Yes, that's a good question. The XRD is a very versatile technique, and you can accommodate with almost any quantity of material. So if you have extremely small quantities, like even down to 1 milligram or 5 milligrams, you can place the sample on a specific sample holder that produces very low background, and so then measuring a few particles on top of that low background sample holder gives you excellent signal and gives you a good analysis from a few micrograms. Then if you have larger quantities like 1 grams or 2 grams, you can prepare a regular sample. And if you have bigger samples or bulk material, that can also be analyzed. But the overall XRD is going to measure about a diameter of about 1 centimeter and the depth of 10 to 100 micron, depending on the type of material. So in terms of volume, it's not a bulk massive analysis, but it will measure some volume. But in terms of sample quantity, you can handle from extremely small quantities, including to measure them in transmission, or you can measure also bulk or larger quantities of material without much problems.
Great, thank you very much. Right into the next question, it's related to PFIB, and the question is, can we use PFIB to cut polysamples or only metal materials?
No, we can cut any material with PFIB. It depends only what current we're going to use. For metals, we can go high currents. For polymers, even biomaterials, we need to go lower currents. So yes, we can cut any material.
Right. Thank you very much. The next question is, what are the key differentiators between XRD and XRF?
Yes, back to me. Those are two X-ray based techniques, okay, XRD and XRF, but they give a completely different type of information. So in X-ray fluorescence analysis, you measure and you obtain the elemental composition of the sample. So you will have a reply in terms of 64% titanium, 5% vanadium, and element by element you get the percentages, but you will not know in which structural arrangement these elements are in the sample. So by XRF, you will not know if the sample is metallic iron or if it's iron oxide or a form of different forms of metallic oxide or iron oxide. So in XRF, you measure only elemental composition and chemistry. In XRD, you have access to totally different type of information. You obtain the crystalline structure, so the arrangement of the atoms. And in XRD, you don't have a measurement of the elemental composition directly, but based on the structural information of the sample, normally a given structure has only a few possibilities of which atoms can be in there. And so by identifying the structure, normally you can identify the compound, and that compound is normally a given unknown chemistry. And X-ray diffraction also performs a different type of measurements, not only for crystalline structure, but you can also compute not particle size, but crystallite size. These are the size of the diffraction domain, and so some other information about the orientation of the particles and the crystals. And so you have more structural and crystal-related information with XRD, and you have elemental information from XRF. So those are really two complementary techniques.
Right. Thank you very much. I have another question on the topic of XRD. What could you suggest for quantitative analysis, XRD or porous samples?
On porous sample. Yes, I think if you say if the sample is a solid material with pores, then you can just measure the sample as it is. I mean, depending on the size of the pores, if the pores are very small, then they will have almost no effect on the analysis itself. So XRD is going to measure the material that is not part of the pores. Then if you have sample that is mesoporous, that is with very, very fine pores, then with X-ray diffraction, it's actually possible to measure the size of the holes. So if the holes are organized with a regular structure, like is frequently the case with mesoporous materials, and then X-ray diffraction also measures the holes, which is a bit funny because XRD measures crystalline structure, but crystalline structure of empty space as well.
Right. Thank you very much. We are almost running out of time for Q&A. Just a few more questions. One question is, what is the smallest voxel size of CT data we can obtain using the standard and advanced correlative holders?
Thank you for the question. So currently, with a advanced holder, we can go down to below 400 nanometers in 2D resolution, and for the standard holder is about 1.4 microns.
Right.
With a 2D. Voxel would be slightly bigger in terms of voxel, three-dimensional, smallest element. Okay, thank you.
Right. Right, and the last question for this session, how long does it take to register the 3D teeth stack in maps using 2 or 3-point alignment? And how can we view the CT data in Z direction?
Okay, thank you. Yes, once we have the stack generated, then the registration is takes well, depends on the size of the stack. Usually it's in order of several hundred megabytes data. Usually it takes a minute or half a minute to load, and then alignment it takes probably 20 seconds. You just need to point the same elements on a SEM images and then on a CT stack data on a particular plane. And yes, how we can view it? We can browse 2D images, CT images. So slide by slide, we know the voxel size, so we know the distance between each planes, virtual planes. So we can view XY as same as on SEM, and then by looking at particular plane, we can see the features in a CT in that direction. Okay, thank you.
Right. Thank you very much. Just one more very quick question, very relevant question. Can XRD work in atmospheric pressure, and can the surrounding gas affect XRD results?
Ah, yes, good question. Maybe this was not perfectly clear in the presentation, that the most of the time XRF instrument will work under vacuum, or you have other atmosphere also for helium, or sometimes you can work under air, but it has limitation for which elements you can then measure. XRD almost always works under air environment. So then you measure your samples under the normal lab condition, and that is the way most instruments will work. Now, if you have a sample that is air sensitive, so that is sensitive either to oxidation or to moisture, you can also prepare samples in a specific sample holder that will protect the sample from the environment, and then you can measure your sample in whichever conditions are required. So you have accessories in XRD that let you measure samples that are sensitive under vacuum, under nitrogen, or under other gases, so you can fill in the chamber with other gases if you like. So XRD in itself is not affected by the environment, so it's kind of irrelevant which gas is in the instrument itself. But if your samples are sensitive, then you can use specific sample attachments that will protect the samples from the environment.
Right. Thank you very much. I would like to thank everyone who joined the session today. We kindly invite you to visit our virtual booth and the networking lounge before you join the next session. If you do, thank you very much for attention, and we are closing the session.
Thank you.
Thank you. Have a good day.
Thanks.
Thank you. Bye-bye.